Welcome to my classroom. In this chemical process calculation course, in this lecture, we are going to discuss about single and multi-phase systems. Single and multi-phase systems. Okay, if we're coming to single phase systems, we have seen that for a single phase systems, how ideal gas equation of state is can be applied, and before mid semester itself, we have covered it in the previous model, how to make use of ideal gas equation to determine the volume required or volume change or work done, all that. Okay, so if we, and we have seen the definition of Dalton's law, Amagat's law also earlier. Okay, so coming to the real gases, what is a real gas? Most of the ideal gases, when you look at ideal gas behaviors, not all the solutions conform to the assumptions made in ideal gas law, because there are several assumptions made, but there will be, we have to make consider some corrections for pressure term, we should consider some correction for volume term. Okay, so we are going to see some compressibility charts and what is a mixture of real gases. Then we are going to discuss about what are the characteristics of ideal gas, ideal solutions. Say for example, what happens, what is the nature of its chemical nature, whether when it is pure substance, when it is in liquid, either what happens with the evaluation or absorption of heat for ideal solution. So all that we are going to discuss, and we are going to discuss in detail about Raoult's law, what is Henry's law, Raoult's law, what is compressibility factor, what is critical temperature, critical pressure. Okay, so we are going to discuss them in detail in this lecture. Then we will move on to vapor liquid equilibria. Vapor liquid, we can even calculate vapor liquid equilibrium data for using Raoult's law. Okay, and what is for an ideal gas solution, how we can express these things. And finally, in this lecture, we are going to discuss about humidification. What is humidification operation and dehumidification operation? How to make use of humidity chart if two parameters are known. How to make use of them to determine the other parameters. Okay, so that's what we are going to discuss in this lecture. If you look at single phase systems, if it is gas phase or liquid phase or solid phases, so we have seen there are some governing equations there. Like for example, for gases, we have equations of states, and well-known equation of state is ideal gas law, that which says PV equal to nRT for when n equal to 1 mole we have, or when V is divided by n we have PV equal to RT, right? So actually in the previous lecture we have discussed before, in the previous model itself we have discussed about what are the assumptions made in the ideal gas law, right? So the gases which obey ideal gases or ideal gas law is called ideal gases, right? And in reality the ideal conditions do not exist, because actually some of the volume, each molecule will occupy some volume, so that we have to take into consideration of correction for volume, or for even for pressure we have to make some corrections. Okay, so there are various equations, real gas equations of states available for real gases. For example, for real gases we can define a compressibility factor. What compressibility factor is defined as Z equal to PV by RT, and for ideal gases is Z equal to 1. Okay, so that way compressibility factor is defined. Okay, we have the definition of critical temperature. What is the critical temperature? It is the maximum temperature, at which the gas can be liquefied. Okay, gas can be liquefied. This is the maximum temperature to which this gas can be liquefied. What is the critical pressure? It is the saturation pressure corresponding to this critical temperature. Okay, pressure corresponding to critical temperature Tc. This is Pc. Okay, and we are going to have critical volume. So that is the volume occupied by the gases. Critical volume, if you want to define, what is critical volume? It is the volume occupied by gases, at critical state. That is at critical temperature and pressure, at critical Tc and Pc. Whatever is the volume occupied by the gases, that is called critical volume. Okay. one should know that the temperature above the critical condition, a gas cannot be liquefied. Okay, above this critical temperature, no gas can be liquefied regardless of the pressure. Whatever may be the pressure, if the temperature is above critical temperature, that gas cannot be liquefied. Okay, so and we have a case rule which states that at this critical parameter, no, if you want the critical parameter of the component, we can say pseudo critical property of a component in a mixture, critical property, pseudo critical property of a component in a mixture is equal to its mole fraction. Let me, so I is the component, its mole fraction multiplied by the critical property, of the component. So where we will be using this is, for example, we have pressure, we have a component A and B in a mixture. Okay, we have a component will have a critical temperature and critical pressure. Okay, this component will have a critical temperature and critical pressure, right? So PCA, right? So if let me say this composition is 0.4, mole fraction is 0.4, and this mole fraction is 0.6 in a mixture. So then to get the composition or the product in a mixture of the if you want to get the property of a component in the mixture, or if you say I want to determine the critical temperature of the mixture, temperature critical of a mixture can be determined if you know what is the critical temperature of A, critical temperature of B, its mole fraction. So we can say that XA TCA plus XB TCB. Okay, so it is for binary. What if it is a multi-component? So we can say in general I equal to 1 to n, whatever is the number of component present, xi into TCI. Okay, similarly PC also can be determined as same way, critical pressure of the mixture will be summation of I equal to 1 to n xi into PCI. Okay, these two are important if you want to determine the critical values for a mixture. If it is pure component, we are going to make use of TCPC values, but if it is a mixture, for example, it contains A and B, in such cases we will make use of the average TC, which is calculated using this formula. Okay, that rule is case rule. We have to make use of case rule to determine the property of a mixture if individual properties are known. Okay, now we have several real gas equations available. Okay, so for example, all these are derived expressions. Okay, so these real gas equations of state are attained. It takes into account some correction term for change in volume, actual volume and actual pressure. So we have this expression P plus A by V square plus V minus B into RT equal to RT, where A and B are Vander Waal constant. A is given by 27 by 64 R square TC square by PC. PC is critical pressure, TC is critical temperature. B is 1 by 8 RTC by PC. Okay, so this A and B will have the corresponding unit. Okay, if you simplify, you will come to know what is the unit of this A and B. They are not unitless quantities, they have unit. Okay, so substituting with the proper unit, this is your specific volume. It is V divided by N. That is your V by N. Okay, that is meter cube per kg mole. That is this value. So P plus A by V square into V minus B equal to RT is the Vander Waal equations. And this A and B are Vander Waal constant. If TCPC is known, we can, of the component will be there in the literature. With that, we will calculate A and B and substitute here. And we can determine either pressure or V if one of the parameter is unknown. V, P, V, T will be there. A and B data. So totally we have A, B, P, V and T. 5 parameters are there. Okay, so out of that, A and B will be obtained using this formula. So remaining three parameter among P, V and T, we can determine the one of the unknown parameter. For example, if P and T are given, what is the volume? Or if volume and temperature are given, what is the corresponding pressure? So like that, we can determine using this Vander Waal equations. Okay, and there are similar to Vander Waal equation, there are other correlations like Benedict-Webb-Rubin equation, which is an 8-parameter equation that states relates the physical properties of same PVT and N for a gas. And there is a Holban method, there is Kamerlingh-Onnes method, Peng-Robinson method, there is SRK method. Okay, so these are some of the names familiar with thermodynamics people, where these equations are used depending upon the situation. So they take into account some of the parameter, and each model is applicable to certain limitations. Okay, so that can be referred to the textbook Himmelblau. Okay, so this is again in Peng-Robinson method, where you have an expression with constant E and B, and expression for A and B is there. Okay, each equation is an some advanced version of the previous version. Okay, so for example, Van der Waal equation is an modification in ideal gas equation, and this Robinson method, all these methods are further improvisation of the equations. Okay, and you can refer to these are some of the equations. So if data is given, we should be able to substitute them in these equations, correlations. Okay, and for with respect to determining the vapor pressure of a mixture, there are several equations are available. To data is there. If we, for example, if we use the Clapeyron equation, if we simplify it, making some assumptions like latent heat of vaporization is constant and independent of the temperature, molar volume of the liquid is negligible and compared to that of vapor, the vapor behaves as an ideal gas law. So then this Clapeyron equation can be integrated to get an anti-ion equation, which is natural log of P, PAS or P star, okay, PAS whatever, is equal to A minus B by C plus T, where T is in Kelvin. A, B, C are constant for each substance. You can refer to literature for complete list. So there are around 5,000 chemicals values of A, B and C are listed in the textbooks and literatures. Okay, so there is another way of determining the data for water vapor, at least for air water system. It's a well established system, particularly for mechanical engineers, or we can say refrigeration units, where humidification operation is being carried out. So if we know the corresponding pressure and temperature, we can get the value of specific volume data of metric cube per kg. So such data is possible, or you can even know the if pressure is known, what would be the temperature. If water is saturated, then what would be the temperature? Like that, we can get the unknown data. Okay, so this is from steam table, you can refer. Okay, so there are several tables available in the similar fashion. Okay, if temperature is known, what is the corresponding pressure can be obtained. So in this diagram, in this table we have pressure, what is the corresponding temperature and corresponding specific volume of the liquid and vapor. In this case, if temperature is known, there will be 4 5 page data will be there, from 200 to some 500 degree. Okay, so from 100 onwards you will have data. So what if you know the temperature is given, what is the corresponding pressure you can take. Okay, or if pressure is given like 1.388 kilopascal, so what will be the boiling point of water? It will be 285. Means what is the boiling, what is the temperature of the water vapor? It will be 285. Like that you can get data. Okay, and this chart is called as Cox chart. So this is the chart which gives us the vapor pressure of the compounds other than water. Okay, so you can, in comparison to water, we are having heptane, acetone, propane, ethane and carbon dioxide. Okay, so this is made in a log graph. You can see the data changing from sorry. You can see the data changing by one order of magnitude. 0.1 multiplied by 10 is 1, 1 multiplied by 10 is 10, 10 multiplied by 10, 100, 100 multiplied by 10. So that means one order of magnitude there is change with each scale. Okay, so this is similar to your friction factor chart that you are learning in your FPM course. Okay, so this Cox chart also can be used to determine the vapor pressure if it is within the scale. Okay, so here we should take care. It is log 10 base scale of vapor pressure. versus temperature is in Fahrenheit. Okay, pounds per square inch. Fahrenheit is the corresponding units for the data. Okay, so we will solve some numericals on Vander Waals equation. Okay. Okay, we will solve a numerical on Vander Waals equation. Vander Waals equation numerical. Okay, take down. CO2 weighing carbon dioxide weighing 1.10 kg occupies a volume of 33 liters at 300 Kelvin. Calculate the pressure. Calculate the pressure using Vander Waals equation of state. Vander Waals equation of state. EOS refers to equation of state. Just using Vander Waals equation of state. Okay. Now data is given for CO2. A is given as 3.6 meter cube whole square by kilopascal kilomole square. Okay, and B is equal to 4.3 into 10 power minus 2 meter cube per kilomole. So we know that PV equal to nRT, and considering the things, we have the expression for this. What is that? P plus n square by V square A into V minus NB is equal to nRT. Okay, we know ideal gas law is PV equal to nRT. So if we consider the pressure correction factors and volume correction factors, we get these expressions. So if we are considering volume per meter cube, that is volume per mole, kilomole, that is molar specific volume, right? What is the name for it? If we are considering molar specific volume, okay, when you say specific volume, it is meter cube per kg. If it is a molar specific volume, it is meter cube per kilomole, right? So in that fashion, if you want to write Vander Waal equation, we have Vander Waal equation equal to, because this is this, right? So we can simply write P plus A by V square into V minus B equal to RT. Okay, so this is the Vander Waal equation, Vander Waals equation of state. Okay, so where A value is given in this problem, usually A and B we have an expression in terms of critical temperature and critical pressure, right? So we should able to make use of this directly now, because A and B value are given. We are asked what is the pressure. So let us write the known data here. What is the basis if you start solving the problem? This is general what I have told you so far. So if we consider a basis of, it is given 1.1 kg is there, right? We have a basis of 1.1 kg of CO2, but what we want is small v, right? So we should know what is the corresponding moles, right? So what is the molecular weight of carbon dioxide? 6 into 32 plus 12. So we have 44 kg per kilomole. So this 1.1 kg is equal to 1 point, I can say that here, I can do that calculation. 1.1 divided by 44 kg per kg mole, we get this much kilomoles, right? So that is the n value. Okay, what is the n value? N value is equal to 1.1 divided by 44. Please use your calculator. 0.025. Okay, so we have 0.025 kilomoles to be the this thing. So we can, volume is given, right? Volume is given like 33 liters something. What is that? 33 liters is the volume given. So what we want is meter cube. So volume is 30 liters, and we know that 1000 liter equal to 1 meter cube. 0.033 meter cube. So what is V? V is volume by N. So 0.033 meter cube by 0.025 kilomole. We get molar specific volume in meter cube per kilomole. What is the value? 0.033 into this. 0.033 divided by 0.025 is equal to 1.32. Please check your own 1.32. Okay, that is our in value. So now what we have to determine is, we have to determine the value of P. So let us write that all the terms here. P is equal to what? What is P value? We have to determine. Okay. Remember, A and B values are given with kilopascal units. A is given in kilopascal unit, B is given in meter cube per kilomole. So there won't be any much issue in this problem. The V value is 1.32 meter cube per kilomole. Okay, and A value is given. A value is given 3.6. B value is given 4.3 into 10 power minus 2. Okay, what is R value? We know R value is 8.314 kilopascal meter cube per kilomole Kelvin. So sometimes we may have to substitute in kilopascal, but if A value is in megapascal, we have to substitute in megapascal. So further into 10 power minus 3 megapascal we have to add. Okay, so take care of that consistency, unit consistency there. So substituting in the equation, P plus A by V square into V minus B is equal to RT, right? So this is the only unknown parameter. You can substitute P plus 3.6 divided by V is 1.32 into 1.32 minus 4.3 into 10 power minus 2 is equal to 8.314 into temperature. What is the temperature here? 303 Kelvin, 300 Kelvin, right? So we have 300 Kelvin. So the only unknown parameter is P. You may get a quadratic equation. Okay, so we have to simplify to get the P value. Okay, so P value you will get in terms of kilopascal, because we are substituting the values in kilopascal. You can write what is the corresponding megapascal. Okay, please comment your answer. So you will get, actually as per this equation we will be getting in kilopascal. Since the value is more than 1000, you can substitute in megapascal. Okay, you will get around 1.5 to 2.5. Okay, so take down this problem. Next problem, 1 kilomole of a mixture, 1 kilomole of a mixture containing 0.4 mole of nitrogen and 0.6 moles of C2H6 ethylene occupies a volume of 90 liters at 293 kilos. Just note down the given data. So this is a gas mixture is given. The previous problem what we did is pure substance. Here we are doing a mixture. Okay, so we have a mixture. That means critical parameters has to be calculated as per their respective mole fractions. That is the law which we referred, right? So we have this occupying a volume this temperature. What is the pressure in the vessel? What is the pressure in the vessel? Use the Vander Waal equation. Use the Vander Waal equation of state. Okay. So data is given. So here data for the individual components are given. So for component C2H6 and the nitrogen, critical temperature in Kelvin, critical pressure is given. Okay, 305.4 to 126.09, 4.880 and 3.394. I think this is in megapascal. Okay. Okay. So now how to solve this problem? So we have TCPC value of the individual components, but we are having a gas mixture containing 1 kilomole of gas mixture. That will be our basis. Okay. So we have 1 kilomole of a mixture containing 0.4 mole of nitrogen and 0.6 mole of C2H6 occupying a volume. So we can find out of 1 mole, 0.4 is the nitrogen. Out of 1 mole, 0.4 mole is nitrogen and 0.6 mole is C2H6. Therefore, mole fraction of A and B can be determined 0.4 by 1, 0.6 by 1. So that is your mole fractions, and data is here. So you can determine the value of the substance. You can find out the TC of the mixture or TPC of the mixture first. Okay. So let us solve this problem. So first we should take a basis at 1 kilomole of mixture. Yes, given it is 1 kilomole. So we are taking 1 kilomole as the mixture as the basis, which contains nitrogen as well as C2H6. Okay. So this is 0.4 by 1, which is 0.4 moles by moles, 0.4 kilomoles by 1 kilomole. So we get fraction. Okay. Mole fraction is this. Similarly, mole fraction of this is 0.6 by 1, which is 0.6. So we have mole fraction of each component, and temperature is given 323 Kelvin. Volume is given 90 liters, which is into 10 power minus 3 meter cube. Okay. Temperature is given, volume is given. What is the pressure is a question. Okay. So first find TC mixture. Because using TC and PC of the mixture, we will be determining A and B value, right? So we have equation for TC mixture. What is the equation for TC mixture? It is summation of I of xi into TC of I, right? Similarly, what is the pressure of the mixture? Critical pressure of the mixture, again summation of I xi into critical pressure of the component. Okay, summation. So it's only two component system, so we can easily determine them. Okay, and after determining this TC mixture value and PC mixture value, you can determine the A value. Formula, what is the formula for A? A is equal to 27 R square TC square by 64 PC, and B value is equal to R by 8 TC by PC. Here PC is given in megapascals. Okay, so therefore we have to substitute R value in P is equal to how much megapascal is the question, because your data is given in megapascal. Okay, since this data is given in megapascal, so we have to make use of R value. Okay, so we have to make use of R value also in megapascal, that is 8.314 into 10 power minus 3 kilopascal meter cube per kilomole Kelvin. Usually 8.314 kilopascal meter cube per kilomole Kelvin, which we know. So we are just converting that kilo to megapascal, therefore into 10 power minus 3 megapascal. Okay. So that's what we have. So substitute to get what is TC mixture value. TC mixture can be calculated as 0.4 into the value plus 0.6 into its value. Here also 0.4 into value plus 0.6 into value. What is the data given? 0.4 into 3.394. It is 0.6 into 4.88. Here it is 0.4 into PC mixture, and this is TC mixture. This is our megapascal. Okay, please proceed to get the A and B values. So we have R value. Remember, we have to substitute in megapascal. That is our care you have to take when you are substituting R value, because PC is given in megapascal. Okay, so we are getting PC mix value. So whatever value you get, you substitute, and you will get around A and B value as 0.3713 meter cube whole square megapascal by kilomole whole square. So that is a unit of A. Similarly, you will get a value of B for B as 0.05655. Okay, so these are the values for A and B, and we have the condition total pressure only we don't know. So we have what we have to find now. P is no unknown, R value is known, temperature is known, and small v value known. Okay, small v is what? Okay, it is per mole only, so we can take per mole 0.09 meter cube per mole. Okay, so that also we know. Okay, substituting. What is our basis here? Check for our basis. It is 1 kilomole. Okay, so that means small v equal to V by N, which is 0.09 by 1 meter cube per kilomole. This is your V. Okay, so we know all the values. Substitute in equation to get Vander Waals equation of state is P plus A by V square into P minus B is equal to RT. Okay, so substitute A value we got, P value we don't know. So P plus 0.3713 by small v value is 0.09 square into 0.09 minus B value is 0.05655 equal to R value again 8.314 into 10 power minus 3 megapascal meter cube per kilomole Kelvin into temperature. What is the temperature in this problem? 323. Okay, solving you will get P value. So please comment your answer. What is P value? P equal to this much. Directly you will get in megapascal. Okay, so please comment your answer. Okay, so that's how we should be able to solve more numericals on Vander Waals equation of state. Okay. Okay, moving on to the next topic, vapor liquid equilibria. So in that we are going to discuss about first what is ideal solution. Okay, what is an ideal solution? What are the characteristics of an ideal solution? So we know that. So the characteristics of an ideal solution are, a solution means what? It will contain a solute and solvent, right? So we can say that these are pure substances. So they are present in pure state and they are present in a solution state. So when they are present in pure state like solute or solvent separately, and when they are present in ideal solution, the nature, chemical nature should be similar. Okay, that means when they are present in pure or in solution, their chemical nature in terms of size, in terms of structure, and in terms of chemical nature, the components, let me say A and B, their behavior or their size, structure and chemical nature when they are in pure form as well as when they are in solution, it should be similar. When we talk about the chemical nature, what is that? So it is about the average intermolecular forces. The average intermolecular forces of attraction or repulsion. Okay, the average intermolecular forces of attraction of repulsion in pure state or in this solution should be of the same order of magnitude. Same order of magnitude. Okay, so both should be of the same order of magnitude. And when it comes to mixing, when the solute and solvent are mixed together, there should be no volume change. There should be no volume change, and volume should be only a function of composition. Right? It depends upon how much solute and how much solvent. Volume occupied by solute plus volume occupied by solvent should be giving us the volume. Okay, so there should be no volume change on mixing. Okay, so that is another condition. Remember, none of the ideal solutions have exhibit these kind of properties. Okay, so for example, optical isomers may have exhibit similar chemical nature. Okay, and another property is there should not be any heat of absorption or heat of evolution during the mixture. Okay, when ideal solution is formed by mixing of these constituents, there should be no enthalpy change. There should be no enthalpy change. No enthalpy change and no temperature change on mixing. When we are mixing, there should be no absorption or evolution of heat. Okay, so and another important characteristic of an ideal solution is they will obey Raoult's law, that each components in present in ideal solution will be obeying Raoult's law. So Raoult's law says that vapor pressure of a component is directly proportional to its concentration liquid in terms of mole fraction. Okay, let me say in terms of mole fraction. Actually, this Raoult's law expresses what is the dependency of the vapor pressure of a solvent as a function of its mole fraction. Okay, for example, if vapor pressure is, if partial pressure is Pa, so we have a liquid, a single substance we can consider. So we have a substance in liquid and vapor. Okay, so the vapor pressure Pa in the gas will be proportional to the concentration of that constituent A in the liquid. Okay, so that's what Pa is proportional to Xi. Okay, so we can get a proportionality constant. So with that we will get Pa is equal to Xi into Pis, where Pis is the saturation pressure or vapor pressure. Okay, so we can denote the vapor pressure in different forms. Okay, vapor pressure can be expressed in written as PIS super with subscript, or we can even say Pi power naught. That fashion also we can express vapor pressure. Or simply capital PV also will represent P, this vapor pressure. Okay, different textbook will follow different notations. This vapor pressure is P subscript V. Okay, this way, capital P subscript V represent this vapor pressure. So whatever solutions which obeys this Raoult's law, that is this expression Pi equal to Xi into Pi naught. So with this expression, the solutions which obey this equation are called ideal solution. Okay, practically no solution is ideal. As I said earlier also, the following examples like benzene toluene, N-octane, N-hexane, ethyl alcohol, propyl alcohol, acetone, acetonitrile, paraffin, hydrocarbon, paraffin oil, such combinations may be considered to be ideal solutions. So we can give examples of these as the for ideal gas solutions, ideal solutions. Okay. So practically no solution is ideal, right? And these are some of the examples for ideal solutions. May be considered. These may be considered. Okay. If you look at the vapor liquid equilibria, if you look at vapor liquid equilibria, so we have to discuss about this Raoult's law. Okay. So for if you look at the vapor liquid equilibria, if you are considering a mixture, if you are considering a binary mixture of A and B, if you are considering a mixture of A and B, so we can say that A will have a partial pressure PA, partial pressure B, PB, and it will have a vapor pressure PA naught or PAS, and PB will have a vapor pressure of PB naught, or we can say PBS. Okay. Now, what is PA, PB? PA and PB are partial pressures. Okay, and we know that XA and XB are mole fraction. Let XA and XB are mole fractions. So then we know that from Dalton's law, for a binary mixture, we know that summation of mole fraction is equal to 1. So we can write XB as a function of A, that is, take it to the right hand side, we have XB equal to 1 minus XA, right? So we have, and also we know that YA can be written as, how we can write YA? YA is PA by P, or we can say YB equal to PB by P. This PB can be written as in terms of PA, that's what I told, PA plus PB. Summation of partial pressures is equal to total pressure. So we have that here. Okay, so we can even write that equation. Okay, so according to Dalton's law, we have total pressure is equal to summation of partial pressure. Okay, this is also based on that. Okay, so what is P? P equal to PA plus PB. What is PA? From this equation, from Raoult's law, what is PA? From Raoult's law, PA, okay, here it is there. Raoult's law, PA is equal to XA into PA power S, or PB equal to 1 minus XA into PB power S. Subscript PB S means what? That power S represent it is vapor pressure. PAS is vapor pressure, as I said here, vapor pressure of A and vapor pressure of B. So this is PBS. Okay, this one. So when you substitute this in this equation, PA plus PB, so what we get is P total pressure is equal to, for PA we can substitute XA into PAS plus 1 minus XA into PBS. Okay, that is a vapor pressure XA 1 minus XA. So this is our total pressure P value. Okay, so when we can substitute 1, 2 and 3, so using 1 and 3, what we get is YA is equal to, what we will get, YA equal to XA into PAS by total pressure is XA into PAS plus 1 minus XA into PBS. Okay. Similarly, what is YBS? Using 2 and 3, we can write, let it be XB itself while writing here. So XB into PBS divided by, denominator is total pressure is same, right? So XA PAS plus XB PBS. So if you want to express XA in terms of XB in terms of XA, it is 1 minus XA into PBS divided by XA PAS plus 1 minus XA PBS. So that way mole fraction can be YA and YB can be obtained once mole fraction is known. You can easily substitute to get what is partial pressure. Partial pressure is mole fraction into total pressure, right? So that way if we know the liquid composition, if we know the liquid composition and vapor pressure of A and B, we can get the vapor composition. Okay, in vapor liquid equilibria we come across two systems, where two cases, where in one case pressure is kept constant and variation of temperature as a function of x comma y. So where let A is more volatile component, so this more volatile component, so we have liquid and vapor. So we have a mole fraction of A in liquid phase and mole fraction of A in vapor phase. Okay, so they are mole fraction of mole volatile component in liquid and vapor respectively. And if T is variation, how the temperature varies, the response of T with various composition of X and Y in the solution. Okay, so that can be done. So we have a binary mixture of A and B, where A is more volatile component and B is less volatile component. Okay, and we know that XA plus XB equal to 1, so we can express XB as 1 minus XA. Okay, similarly in vapor phase, this is in liquid phase, liquid mole fraction is expressed as X and vapor mole fraction is expressed as Y. So we can say YA plus YB equal to 1. We can say YB equal to 1 minus YA. Okay, so that way this A can be skipped. Always simply YA comma 1 minus YA or XA comma 1 minus XA are used. Okay, so that way we can skip it to write simply X 1 minus X Y 1 minus I's Y to express the concentration of A and B in liquid phase and concentration of A and B in vapor phase in terms of mole fractions. Okay, so that way we are skipping the subscript A here. Okay, so if you look at a composition, so what we actually get is, let X comma Y is in the X axis and we have T in the Y axis. Okay, A is more volatile component and B is less volatile component. That means we have boiling point, let us say in this fashion. And in this pure A, here we have pure B. Okay, because X equal to 1 means XA is 1 means XB is 0. Similarly, when you say pure B, when X equal to 0, that is when XA is 0, your 1 minus X is 1, that is mole fraction is B. That way, so we have boiling point of B here, means boiling point of pure component B here, boiling point of pure component A is here. Okay, so that is the temperature boiling points. Okay, so this is if we plot T versus X and if we plot T versus Y, we are going to have such set of plots. Okay, so if we have TXY diagram, this diagram is called as TXY diagram. Okay, So what is the use of this TXY diagram? This TXY diagram will help us to know the, if you know the, to know the composition, it helps us to know the composition at a given temperature. Okay, if you know a mixture of A and B, and at a given temperature, what would be the proportion of liquid, what is the proportion of vapor can be determined. Okay, so how, first what is this TXY diagram and how it happens? Let us consider that it will be x equal to 0.5. Okay, so that means XA is 0.5, 1 minus XA also 0.5. In liquid and vapor it is 0.5. So if you consider a point here, we consider it to be straight. Okay, so what happens is, what phase we are having is pure liquid, and here we have pure vapor. Let us say it is V, it is L. So what, below this line we have pure liquid, and below this line we have pure vapor of A. Pure liquid of A is in pure liquid form, A is in pure vapor form. Okay, so at this point, say for example, we initially we have a temperature T initial, and if we start heating this solution of having XA equal to 0.5, at a particular temperature there will be first drop of bubble will be formed. Okay, so the first drop of bubble is formed, and the temperature is called bubble point temperature. And further in this phase we will be having a composition of, we will have a mixture of liquid and vapor in this phase, and here we get a point where the last liquid also becomes vapor, and above which we have pure vapor stream. Okay, so that way we have this time. So this line is called as bubble point curve. Similarly, when we do the reverse process, when you are having a temperature, initial temperature is high where it is only pure vapor, and if you slowly cool that, reduce the temperature of the system, where you, from pure vapor the first drop gets condensed into liquid, so that is called dew point temperature. Okay, so that curve is called as dew point curve. Okay, so this curve is called dew point curve, and we will have the corresponding, this is x, this is y. Okay, so we will, if any parallel line is drawn, for example I have a temperature T, if I draw a parallel line to x axis, so let me change the color. So if I, at a particular temperature I draw a parallel line here, so what we have is, this is the concentration of x and this is the concentration of y. Okay, so we get xy data. So like this, if we drop set of values and set of values, so what we get is, we get x versus y value. Okay, so what we get is x versus y data, so which can be plotted x versus y, so we can get a curve like this. Okay, so this is called equilibrium curve. Okay, another thing that we can know from these tie lines, these lines are called as tie lines, which gives us xy data. Another usage of these tie lines is, another use of the tie lines is, if I know particularly, let me say if x equal to 0.4 and have a particular temperature T. Okay, so what we can know is, what is the corresponding x and y value, how much portion is liquid, how much portion of vapor is there, can be determined. So that way, let me say this is one line, this is the one value, let me say it is A M T. So we can have AM by AT is the L by V ratio, how much liquid and vapor is there. If you know the value, this x-axis value itself, we can determine what is the portion of how much. When means, this will give me like this, if you get this as 2, we can say that there are 2 times liquid to the amount of 2 times the means, for each it's a ratio, not 2 is to 1, L by V is 2 by 1. Let me say L equal to 2 by 1. We can say that For every vapor there is 2 times liquid is present in that this particular composition and at this particular temperature. Okay, so that way we can make use of TXY diagram, okay, to explain what is dew point temperature and bubble point temperature, and also we can make use of it to get the XY curve, and we can, for a given composition of X and temperature given X and comma T, what is the liquid by vapor ratio can be determined from this TXY diagram. So similarly we can have a PXY diagram where temperature is kept constant. Okay, so the PXY diagram we are going to get the reverse of what we are having. Okay, so PXY diagram, P versus Y will be here, P versus X will be, that is the reverse of that we will be getting. So here it will be pure liquid and this will be pure vapor, and this will be your bubble point curve, and this will be your dew point curve. Okay, and in between you are going to have liquid plus vapor. Okay, so again we can draw tie lines at any pressure to get the composition. Same way that can be done. Okay, so that is the difference between TXY diagram and PXY diagram. Okay, so if TXY values are given, for example if T, we should do numericals like plot TXY diagram if X versus Y data is given, T data, X data and Y data is given. Okay, sometimes relationship between Y and X can be given like Y equal to alpha X by 1 plus alpha minus 1 X. Okay, so this way we can get the first XY data at this given temperatures. Okay, and we can plot TXY curve. So you should able to draw a TXY diagram and say this is bubble curve and this is dew point curve. In this lecture we have seen what is real gases, what are the equation of states like Vander Waal equation. We have solved some numericals on Vander Waal's equation. We have seen what is how Narayanan equations can be used for vapor pressure determination. What is Raoult's law, what is Henry's law, what is TXY diagram, right? How to plot TXY diagram, all that. Okay, in the next lecture we will discuss about humidification chart. Thank you for joining my classroom.